Okay, folks, it's about time to get started. So, welcome to Continuous Profiling, the fourth pillar of observability. Before I'm going to get started, you can see there are some elephants here. You can get one of those if you ask questions afterwards. Okay, so my name is Florian. I am working at Datadog. I'm building a continuous profiler for the PHP language. Besides that, I'm also an open source contributor, and I used to contribute stuff to GraphQLite, which is an amazing library. If you ever end up in a situation where you have to build a GraphQL server in PHP, check out GraphQLite, it's awesome. I also contributed to PHP Unit, trying to do some deprecations. That was a ride. You learn a lot about people, how they're using PHP Unit and misusing it. That was funny. Then I started contributing to some PHP extensions, the PHP documentation, the PHP core itself, the PHP internals book, and 2 years ago I became the co-maintainer of the parallel extension. That is an extension that allows you to do multi-threading in PHP. And I'm doing all of that, although I'm married with 6 kids. There are only 5 on this picture. The youngest one is just 10 weeks old, so she wasn't there with us. Okay, what is observability? I mentioned in my talk that continuous profiler is the fourth pillar of observability, so what are the other 3? And with that, we are going through those pillars, and I also brought you a problem that I had. So the first pillar, or the first signal that you can get out of observability is metrics. A metric is a numerical value representing something at a specific point in time. And that something could be the CPU utilization, the memory utilization, the latency of a request that you just had, or that there was a request at this point in time, the numbers of messages in a queue or something like that. And I had to monitor a service. This is the latency metric for a service. And you can see in the beginning, the timings were in the, I don't know, 30 to 100 milliseconds area, and then they started to ramp up. This is already like 6 seconds, then it was between those 2 and 4 seconds, and ultimately the latency for the service went up to 11 seconds. So that was something to look into. Because metrics didn't tell me what actually was happening, not why things were happening, just that here's a metric, your latency is bad, do something about it. So I checked the service, or the logs of that service, which is the second pillar, or the second signal that you can get in observability. And logs are time-ordered records of discrete events that describe what the system did and why it did it, although I have to say that what it did and why it did it stands and falls with what the log message is. If, like in this case, the log message is just CSV import finish, then there's not a lot of stuff to read about and why things happened or what could have gone wrong and so on and so on. So yeah, so the logs are not really useful here, but there are 2 things I want to say about logging. First of all, there are 2 different kinds of logs. There are infrastructure logs and application logs. Infrastructure logs is everything that supports your application, like your Apache, your load balancer, your database server, PHP FPM. All of these tools are writing logs somewhere that you can collect and you can look into. But all of this is infrastructure. It's not telling you about what happened in your request. Then there are application logs, that is what you write about. Ideally, you would structure logs, like in JSON, like with this here. That means that you can search for specific values in here. It's a bit hidden here, but you have the context user ID, so we can look for the user ID and filter, so we just see all of the logs that this single user created. So logs told me basically nothing here. I knew from the metric that we had a problem with our latency, but logs didn't show me any errors or any problems at that point in time. So the third signal that I can check is traces. A trace is a full execution path of a single request across your entire system. So it begins whenever the HTTP request, for example, reaches your intake or your edge, let's say a load balancer in AWS, and from there you forward it to whatever pod you have running with Nginx, and that Nginx forwards it to a PHP FPM daemon that executes your PHP script, and that talks to a database, downstream services, whatever. Traces are composed of spans, these things here, these wide things here, and the smaller ones here. And each of these spans represents a unit of work. And that unit of work is the incoming HTTP request from beginning to end. And it's a function or a unit of work, a block of code that we want to observe. And then we also see two database spans in here. This is queries to MySQL, and we see those queries start at the beginning of that CSV import stuff, and they end at the, I think the microphone is gone. Okay, and they end at the, they send another MySQL request at the end of this trace. So what we can see from this tracing here is that we get HTTP request. This is the thing that is slow, and we can see it's taking like roughly 15 seconds overall, the entire span. We have no idea what's happening in there, but at least that's something, so we know where to look further. And this finally brings us to the fourth pillar of observability. The first three pillars are very well established already. Profiling is the four signals, and where logs, metrics, and traces can tell you that something is wrong and can tell you where in the request. Profiling can tell you why something is happening. Actually down to the line of code, what burned resources. Because profiling is different in a way that it is showing you the world from the engine's point of view or from the CPU point of view. It's not showing you what you wanted your code to do, but it's showing you what the CPU or the send engine in our case actually did to execute the code. And yeah, the question is, how is it doing it, or how is the profiler doing this? Well, by collecting stack traces. A stack trace is usually has bad reputations because usually you see stack traces when things go wrong. Like we have a division by 0 here, and what we get is we get a nice stack trace for that. But as the saying goes, one man's trash is another man's treasure. Because profiling loves stack traces, that's what we do. But how do you get a stack trace in PHP? Well, usually languages offer an API for you to collect stack traces. In Go, you have debug.stack. In PHP, we have debug backtrace, which returns you an array with the stack trace of how you ended up here exactly at that point. There's also debug print backtrace, which will just print it out and basically produce the result that we saw earlier. And you can also give it some arguments to tell it if you want to see all the arguments of the function in the backtrace. You can also collect all of them. So a profiler is a tool to collect stack traces over time. How is it doing it? Well, we check the state of the application, or of the PHP VM in that case. We do collect a stack trace, so we now see that at precisely that point in time, there was a main function that called serve request, that called get balance, that called dbselect. That's the current stack of what PHP is currently doing. Then you do this 100 times a second, so 10 milliseconds every 10 milliseconds. So just 10 milliseconds later, we check again what is PHP currently doing, and the stack trace looks different. We see a main function that called into report to IRS. And if you do this over time, sooner or later, you're going to see the exact same stack trace or one of the stack traces again that you already saw. Now, one way to analyze stack traces is that you can aggregate them into a profile and basically just saying we saw this stack trace twice and we saw this stack trace once. Given enough stack traces over time, the profile becomes statistically representative of the average program behavior. Now what we have like more time. We observe the application for a longer time, so we see different stack traces in here. We see that the stack traces have been executed 30 times, or we observed it 30 times, this being the active stack trace every time that we checked. Now a different way or another representation of the sample is a weighted tree. And the numbers are really bad to see here, but well, I'm gonna explain you. The basic idea is that every node that we have in this tree represents a function that we have observed in all of the stack traces. So we have observed the main function. From the main function, there are two nodes going to report to IRS, which ends and serve requests. From serve requests, overall, we have two nodes going to get balance and make deposit. That's the two functions that serve requests can call into, and get balance goes into dbselect and make deposit into dbinsert. And we give them values, and each tree node is assigned the cumulative number of times the function has been seen in all the stack traces. So the get balance function, this is a 50 if you don't see it. The get balance function has been observed 50 times overall because we see it in this stack trace and we see it in this stack trace. So we just assign these numbers and then we know how much this function weight. Now the thing is, a weighted tree can be visualized differently by turning each node into a weight length bar. So that's what we do here on the side. The db select function we've observed 30 times, the db inside 20 times. So we make this 20 wide and this 30 wide, whatever that is in the end. And if we remove all the helping lines here, what we get is this thing, and that is a flame graph. And this flame graph visualization was invented by Brendan Gregg. One thing to note here is that the order of the functions you see in the flame graph is not by execution time, but it's usually alphabetically. You can also order it differently. You can also order it by the length so that you see the let's say most interesting stack traces first. And what we just did, the thing we just built, that is a sampling profiler. We are grabbing stacks periodically, then we aggregate all of that together, and we do this 100 times a second. All of that is statistically representative of what the program is doing. And yeah, there is a whole other family of profilers that is instrumentation profilers. And the differentiation is basically that an instrumentation profiler, the idea is that it depends on when you collect a stack trace. A sampling profiler would collect a stack trace, let's say, every 10 milliseconds, or not as often if you don't need as much resolution. And a instrumentation or tracing profiler does collect a stack trace on function entry and on function exit. Basically, you hook every single function call in an instrumentation profiler. The benefit you get from that is that you get absolute exact call counts, and your timings are at least relatively absolutely correct to what's going on in your system. But the problem you get with that is you get extremely high overhead for that. There are two profilers out there that are tracing profilers. There's the Xdebug profiler. So if you have Xdebug already installed, it's not just a step debug, it also comes with a profiler. The profiler dumps out cache grind files that you can then open up in kcache grind and qcache grind. I think there's also web cache grind or something. That you can open up those files and you see everything that was happening in this one request when you had the Xdebug profiler collect data. There's also SPX, which has a nice web UI that it ships with. So you just install the extension, and then you have a specially crafted URL that you can go to, and then you have a nice web interface that will present you flame graphs of the stuff that it observes. Usually that's also tracing. You can configure it to do sampling, but technically it's just a tracing profiler. The thing is, a sampling profiler just does periodic snapshots, stack snapshot. That means that it's approximate but statistically correct, but it also means that it's very cheap to do all of this work. Anyone here from the Java community? Anyone know Java? Okay, so you might have heard of the Java flight recorder. The Java has a flight recorder that is just called JFR, the Java flight recorder. And the nice thing about it is that I would say continuous profiling is basically a flight recorder for your code. It's always on, it's low overhead, it's recording continuously. And when something goes wrong, you can actually go back to what happened and can look into what was going on. So basically, if a Java application dies, you can poke the JFR file and find out what was happening at the time everything went south. Because the problem is you cannot attach a debugger to a production incident after the fact, because like your servers are already down or whatever happened already happened. You can't do this anymore. And the flight recorder can capture all of that for you. I'm always talking about doing this continuously and doing this in production, but why do we want to install a continuous or profiler at all in production? Well, the thing is basically just this, because staging is not production. And some of the behavior of your code you will only be able to observe in the massive reality of your production environment, nowhere else. So back to our problem. Metrics were showing us that we had a spike in latency. Logs were not really helpful because we didn't write good log messages. And the tracer would just show us that in this one service for these kind of HTTP requests, we would spend a very long time in those spans, but we have no idea what we were doing in there. So I opened the profiler, And this is small on purpose. We're going to zoom into it. You can see that, I'm going to show this later on the next slide. You can see this is very deep. This is, I think, 85 frames deep. So something is happening down here with exceptions. And when we look at this, we see that the profiler saw in those 14.2 seconds, what basically the trace span length is, the profiler observed that we were throwing nearly 500,000 exceptions. If we go down to the end, we see these are the two functions. There's a scalar comparator and an array comparator function, a class that we call an assert equals on, and that throws a ton of exceptions. So if we do the math, that is 35,000 exceptions per second. That's a lot. I would say PHP is fast. But the log showed success, and also the tracer showed success. That is because we didn't log those exceptions, and that is also because those exceptions did not travel the boundary of a trace, so the tracer did not observe them. That means they were caught in the code. So let's check the implementation. That is the function call that we were doing. There's a comparator class, or an instance of a comparator class. We call an assert equals. We give it the expected and the actual function. The interesting thing here is the signature of that function, and that is it returns void if everything is correct. But if it's wrong, if the assertion doesn't match, then it throws a comparison failure. That is a horrible idea to do this in production. And the idea or the problem here is that this was a library used in another library, like down the way. And this is from the PHP unit ecosystem. This is the Sebastian Bergmann comparator library. And in PHP unit, that makes totally sense. Because if you do an assertion and that assertion fails, you want to throw an exception, bubble all the way up, and just do not do anything anymore in this test because the test failed now with that assertion. You want some extra information. The comparison failure exception gives you some extra information. And in the PHP unit ecosystem, this makes totally sense. In a production setup where we actually need to compare two values, this is a horrible idea to do. Why are exceptions so expensive in PHP? That was the next question. How much time do we spend there, and why is this so expensive? Well, PHP has to capture with every exception object that you create. PHP captures the entire stack trace. It's not doing this in a very optimized way because it should be exceptional. So there's no way to optimize for that. No need to optimize for that. We had 85 frames to walk, and for every single frame, we had to collect the function, the class name, the file name, line numbers, arguments, all of these kind of information. That is just a lot of stuff, and we have to do this nearly 500,000 times because we threw 500,000 exceptions. If you do the math, like I did the math then, and I run a script that does nothing but just throw exceptions in a loop and catch them in a simulated 85 frames deep stack trace, what you get is you get 3.3 seconds of just throwing exceptions out of these, like just 3.3 seconds. So with the 14 seconds, that means that 23% of our total runtime we were just spending with throwing exceptions, where we could have just returned a Boolean false or true. So what happened in the end, once I knew this and once I knew what was the problem, I analyzed what was going on a bit deeper into other log files, and I found out that basically we had a client who had an upload job, a CSV upload job, and that went rogue. So what they did is they started uploading way more CSV files, way more frequently, basically in a tight loop. And those CSV files started to have, when we import them, we do check. So we check some fields against if they are still equal, and they managed to mess up something in the CSV file, and now basically everything was not equal anymore. So we had what used to be a side path or throwing the exception now became the hot path in our loop. So more comparisons failed, and that means that we started throwing a lot of exceptions that we had to handle. So in the end, the code did exactly what we told you to do. This was the uncomfortable part. There was nothing really broken, to say too big. It was just that we had some assumptions about the code that didn't hold up then in production reality anymore. Because observability is not always about catching the big explosions, because if USD's one go down, you'll probably find out earlier than any other observability tool, because they are maybe also hosted in USD's one. So it's about noticing these kind of problems. We've seen that exception profiling helped us here because it explicitly showed us that there is a ton of stuff going on. There are a lot of other profile types around. So obviously we can collect the CPU time that you're spending when you're doing CPU intensive function. You can also collect the wall time, which is interesting specifically if you do like curl requests or something. This won't show up too much CPU time because it's not CPU bound, it's just IO bound. Exceptions, we already have seen them. There's also allocation profiling, which shows you where you are allocating memory or where the PHP engine has to allocate memory to do the stuff that you're doing, which gives you interesting insight, like if you allocate memory in a loop, if you already know how much memory you have to allocate, you can start pre-allocating them, pre-allocating that memory or pre-allocating a big array. If you know a bit about PHP internals, you know how to tweak it a bit and make it pre-allocate stuff. Then there is IO profiling. IO profiling is basically, let's say, a better version of all-time profiling because it shows you where you spend time. Yes? Oh, sorry. Yes. Yeah. I am excited. Okay, sorry. Okay, sorry. Yeah, IO profiling. IO profiling will show you where you spend time and how much bytes you transferred. And it's split up by talking to a socket, like talking to a database, a downstream service, an upstream service, or file IO, like just writing to your file system, or even if you run an include of a file in PHP has to compile that, and PHP doesn't have it in its cache already, PHP has to reach out to the file system, get the file, and so it does a read, and you will see that in IO profiling also, how much bytes it read. And then lastly, there are more profile types, but there is heap life profiling also, which is interesting. Not interesting if you're using PHP FPM, for example, because with PHP FPM you get the PHP shared nothing. PHP will tear down in the request shutdown everything. It will also flush the send memory manager. So whatever you had alive will be gone by the end of the request and won't leak into the next one. But if you run let's say a CLI worker that consumes messages from a queue and handles all of those messages, and this is now a long-running process, you don't have this request init request shutdown phase anymore. So the send memory manager will not shut down. Or if you run FrankenPHP in worker mode, that's the same problem. FrankenPHP worker mode is pretty amazing of what it can do and how fast it is, but also you don't have the request init and request shutdown phases anymore, so there's no send memory manager collection in the end, where it just throws away everything. So you could leak memory, which is a problem we as PHP developer did not have before, when we just were using PHP FPM and not doing stuff like long-running workers or FrankenPHP worker mode. While we are at collecting information about the PHP process, there are certain things that PHP magically does in the background, which you usually don't notice. PHP can trigger a garbage collection cycle. If you do create enough objects, all of those objects will be registered as a root in the garbage collector. And if there are 10,000 roots, then PHP will trigger a garbage collection cycle. Technically, PHP is a ref-counted language, so every time there are no references anymore to a variable, PHP will just free the variable for you at that point in time. But with objects, you can have cyclomatic references, just two objects pointing to each other. And if there's nothing pointing to the objects from the outside anymore, they're just pointing to each other, then they will stay alive forever because they have reference. The garbage collector is there for exactly to find the cyclomatic references where basically nothing from the outside is pointing inside anymore and then freeze all of the objects for you. You can trigger a garbage collection cycle by calling cheesy collect cycles, but if you don't do that, PHP sooner or later can do it for you. Then there is obviously file compilation. If you include a file, or nowadays we tend to not include files anymore, we just write new some class and have the autoloader load that. But under the hood, basically what happens is there is somewhere down the line, there is an include to a file that will be loaded from disk, will then be compiled and stored in opcache. And then there is one thing that is also problematic is opcache resets. I've seen that most of the customers that we also have do not really tune or configure opcache to their needs. You just turn it on and you run it, and usually it just works. And if you do some benchmarks against it, you see that it makes your script faster. But the problem is if you don't really configure that correctly, of how much memory you need, how much intern strings you have, what will happen is that the opcache is a append-only cache. So once it's full, it will just throw everything away and start from scratch. That means that PHP will be in this endless, I have to recompile everything again loop and waste a lot of time. These are all things that PHP does magically for you, and they take time, and we can collect all of these information and make them somehow visible. And for that, I want to show you a timeline representation. This is with a lot of different sample types. So in the timeline, we can see in gray all the idle phases. So you can see FrankenPHP is not doing anything here in the beginning. There are some blocks where those threads were not doing anything. Then we see the blue line is CPU. So we see all of them are doing something, not a lot of work, but all of them are occupied and doing stuff. This should be red. That's the file compilation time. This is runtime activity across threads. This is an interesting thing because we can see in the beginning there's a small red dot showing us that PHP is doing file compilation. That is when you start PHP, FrankenPHP in worker mode, then it will spawn all of those workers and run to the execute your PHP script and run to the first FrankenPHP handle request. And there it will block and wait, which is this gray thing here. So it will not do anything. And then suddenly the load balancer decided that it's there, and then it can send traffic to this FrankenPHP worker server, or worker mode machine. And you can see the first thing PHP does in the beginning is it spends a lot of time in compiling everything. And then we see, which is not necessarily problematic, but it could be. The thing that is problematic is we see this long yellow line up here in the runtime activity, and that is garbage collection. So if we go here in the runtime activity, we see that this entire process over this 1 minute and 5 seconds or something, spent 19 seconds in doing garbage collection. That is something you would need to look into if you see this. What you can do is you can click on garbage collection, and then you can select the single events, and then the profiler will show you where that garbage collection was triggered. Like, was it triggered from you? Did you do a GC collect cycle somewhere? Or was it induced by the engine because there are too many routes? And then you also get the line number and the file name where this was triggered, so you can actually go there and check out what you were doing at this line in order to trigger a garbage collection cycle. Yeah. So why are we doing all of this work? This is a lot of rainbow colors. It's beautiful. The question is, why are we doing all of this? Well, we're doing this to save money. Because caring about performance maps directly to the cost on the hyperscalers. And there's a second effect, and that is latency usually goes down. So when we make sure that when we see those kind of profiles and we see that, oh, we're spending a lot of CPU time doing this, or we see that the PHP engine decided to do a lot of garbage collection cycle, or in this case, spending 20 seconds, nearly 20 seconds in garbage collection, that is 20-second pure CPU time that is doing nothing for your customers. A garbage collection cycle will completely block your process from responding to the client. So as long as PHP is doing GC cycle, it will not process the request any further. It will wait for the GC cycle to be finished and then do the rest of your PHP code. So all of that will bring your cost down at hyperscalers or in your infrastructure, and all of that will also bring down your latency, so your customers will be more happy. One thing we also did at Datadog is we created a performance win Slack channel where people can post about the stuff that they did and how much, in the end, ultimately how much money that saved. And with some nice screenshots about from metrics where you can see that usually CPU overhead is going down, latency is going down, or just the cost dashboard where you can definitely see that money is going down and we're spending less on machines, or the autoscaler just started downscaling because we don't need all of those machines anymore. The second thing, like performance is great. The second thing why we do profiling is because faster mean time to resolution for problems. We have seen this example from the which ultimately led to find in the exception profiler that we were throwing a ton of exceptions. What you can do is, like, you don't necessarily always have to start with going to metrics, then going to logs. From that, what we learned back then was we can create metrics out of profile data. So we can say for a profile, we know the length of the profile. We also know how much exceptions there have been thrown. So we can calculate a exceptions per second metrics out of that profile and feed that into metrics. And then we get a nice graph that hopefully never spikes up. If it does, we get an alert. So we learned that, let's say like this. The other thing I want to say a bit about the future of profiling. So far, most of the profiling tools that you have seen are from SaaS companies or open source tools like Xdebug or Xdebug Profile or SPX. In May 2022, since May 2022, there is a special interest group in OpenTelemetry about the profiling signal. And just in March this year, the signal has reached alpha level. This is not a one-man show, one person doing. There are people from Datadog, Elastic, Google, Grafana, Splunk, Red Hat, Polar Signals, Shopify, SimTrace, and Adobe working together on creating a standard for a profiling signal in OTel. And the first version of that profiling signal was basically pprof, which is the standard in Go and was provided by Google. Now it's not that close to pprof anymore. There were a lot of changes. You can convert from the one to the other, but they are technically different now. And this is just a signal, so that means that there is a definition of how a profiling payload has to look, if it's OTel compatible, and how to work with all of the data. But there was no profiler. And then a year ago or so, Elastic donated their whole host profiler or their eBPF profiler to OTel. So now what we have is we have an eBPF full host profiler donated by Elastic. That is 1 daemon per node, so you don't install this in your runtime or in your container, but you install that into the Linux kernel that is running the host as an eBPF program. And then on the side, you have a sidecar that collects the stack traces and does the symbolication of all the stack traces for you. And what that also means is that you get native and interpreted stacks side by side, which is a good thing. And the overhead is just 1% roughly of what you're adding or what you're paying in CPU to get all of these kind of insights. The downside is that with eBPF, you're basically only able to capture CPU time. So you would still need a runtime profiler if you're interested in wall time or allocations or exceptions or other stuff. But at least for CPU time, you get all of that. And what I want to show you, this is a flame graph of a PHP application that is observed by the full host eBPF profiler. And what you can see here is we can see there is the start of PHP FPM 8.4. That's when PHP FPM starts. Then you see like everything that PHP FPM is doing, the main function of the FPM main, then the execute script, and ultimately it goes to the executex, which is a C function in PHP. And from there it jumps into PHP code. So you can see that this is PHP doing basically all of that is executex. PHP is in the interpreter loop. Then you see like all of these PHP frames, and ultimately you see an opcode handler here. You see another PHP frames there, opcode handler there. So you get all of this mixed up, and you can not only see that you are in PHP calling a function, which is most of it glorified C wrappers, but you can also see what then the C library underneath is doing. So one thing I wanted to show is this small graph here, this long small graph here. This is actually the PHP in-process profiler doing its work. So we see if you click on that, you see PHP still, the C library, you see all the PHP code, and you see PHP is doing a string repeat function, which jumps into CIF string repeat, which is the C implementation in the string.c in PHP internals. From there you can see it's calling a send string save alloc, which will allocate memory, and that jumps into the Datadog profiler, which then just forwards to the send memory manager to do the allocation. And ultimately, this here is when it decided I need to collect this stack trace. That's all it does. It's a tiny part of a tiny part. But it doesn't really end here. Like we have C code in there, we have the PHP code in there, we have a bit of C, we have Rust code in there, and then a bit of C code. What you also can do is you can see what the kernel is doing when you profile all of this. Because what this is, PHP is calling fast CGI finish request in the end. which we call the C implementation, which ultimately calls a libc write function. The libc write function sends a syscall to the kernel to actually handle all the writing on that socket, and then you can see everything that the kernel is doing to handle your syscall. So not only can you see that you were doing something that was blocking stuff, but you can also see if the kernel is overloaded by doing certain things. So what do we do now? After this conference, when you're at home, I would think it's a good idea to just install the Xdebug profiler, get that running, maybe install SPX if you want to do this locally, and just see the profile and see what happens with the data. Observe what you can see. One thing, I don't know about you, we had get a nice, let's say, time budget of doing training for LLM and AI stuff. So what I was playing with was to putting the profile into an LLM loop, which is basically just, there's the source code, here's an HTTP server running, you can send call requests to that machine. So attach a profile, attach the Xdebug profiler, that will profile the stuff for you. And then once you get all the feedback back from the profiler, you know how the stuff is running. So please try to do an optimization and then do the same loop again. And do this until you can't optimize anymore, and like write down a lot of information for me, because otherwise things can get lost. That is something that I have seen is very powerful, specifically in PHP, because PHP is a very, let's say, easy high-level language. So a profiler or an LLM knows relatively good what's going on. And with that being said, that's all, folks. Thank you very much for attending this talk. Are there any questions? Yeah.
Maybe I missed it, but you mentioned the eBPF for CPU time profiling. And how do you do the rest?
You need an in-process profiler. This one, for example. Yeah. Yes, you need a you don't necessarily need a sampling profiler. You could also use a tracing profiler, but you would not want to install a tracing profiler in production. So for that, you would need that. With eBPF, we would need support in PHP itself to, let's say for allocation profiling, for example, we would need in PHP itself to set the eBPF probes so that the kernel knows exactly what's going on there, and then you could start profiling that. But that's not in there. I just on Monday, I opened a pull request to the OpenTelemetry eBPF profiler to support PHP 8.5 because it's not yet in there. Now we get CPU profiles for 8.5 also. You and your elephant. Yeah.
First of all, a joke. You say profilers save money because of the cloud, because there is a cloud. If you have your server.
Yeah, if you have your server, yeah, if you're just on. No, it's true. If you just have one machine running, then the best advice to save performance is upgrade PHP to the latest version.
Yeah.
That's the best thing.
No, curiosity, because you say exception are so slowly.
Yeah.
Are so slowly because they allocate a huge amount of memory, adding stuff like stack trace and so on. There is a way to avoid, if you know, in PHP, to allocate everything, every single exception.
If there is a way to avoid this?
Yes.
No. You mentioned it's doing a lot of memory. You can see here, those 14 seconds, we allocated 31 gigabytes of memory just to create all of that. No, there's no way to do this because if you create a new exception class, if you just do a new exception or a new whatever class that inherits exception, you can, even if you override the constructor of that, there is an internal constructor that is being called, and that collects all of that information. There is no way for you to bypass that.
Okay, no, because the only one time I had to do profiling is simply a tick function to call stack trace
No.
and so on. So really that's
No.
useful. Server are huge loaded, and then when I start profiling, server are super huge loading, and then I
Or we leave it on continuously.
No, I know. You do continuously.
Yeah. Not necessarily to
Request.
for every request, everything. Yeah, that's why we build a sampling profiler. You don't want a tracing profiler for that in production. It's horrible. But a sampling profiler, like the eBPF follows profiler, is just 1% of CPU overhead that you pay to profile everything that is running on that host. Because it's an aggregating profiler, it's not really too much. Yeah. 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 Oh no, sorry, not sorry. You earned the elephant. Yeah.
It's a simple question. So working Datadog, and I can see you're also still using Datadog to monitor Datadog. So
Yeah, we put a profiler in the profiler. We're dog fooding, yeah. 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 It's also that we have a tracer, and the tracer has some integrations in PHP itself. So we are not hiding those PHP frame in the profiler. So if you have Datadog and you see PHP stuff happening, you see the Datadog tracer in there as well. Which means that the tracer team has to look that their overhead is low because we show that overhead. Yeah.
I saw you had a mention of MTTR.
Mhm.
I've seen this mentioned as a change that's been brought about by the use of a lot of AI tools. That we've sort of shifted focus from MTBF to mean time between failures. We're trying to stop stuff going wrong. We've moved away from that instead to making it faster to fix things when they go wrong.
Yep.
By using AI tools. Are you seeing that in your
Yeah, yeah, yeah. That's basically what we are doing. That is the wrong slide. This is the slide. No, the idea is, or what we are doing a lot is you deploy stuff to a staging environment, and there you have an AI looking at the profiles that are happening. So it's not necessarily about just vibe code and ship stuff and let it break and hope an LLM catches it. That's like, you can do that, of course, if you want to. You can do that, but I'm not recommending that. It's a bad idea because customers will go away.
a lot of shifting that because it's like the vibe coding thing is just gone like mean time between failures. Oh, we're going to ignore that. We can fix it really fast when it goes wrong.
Well, it depends, right?
Well, I'm just helping to.
Yeah. Yeah.
So, what's your preference? I know your preference would be probably Datadog.
I'm biased.
What's your preference between XH profile and SPX profile?
I would not use any of that in production. But if you're running it locally, I would probably choose SPX. Yeah. I don't know why. Probably just because it has a nice web UI that it ships with. So you have a special crafted URL that you can use, and then it opens up a web UI, and you can check the profiles that are in there. Also, you can configure it to do sampling. They warn in the README that they are unstable and have crashes with CTS PHP, with the multi-thread version. If you don't run that, then it doesn't really matter, right? Yeah.
One of the things you mentioned is that one of the expensive processes you saw was the GC collect science for PHP. And through all the profiling that you have done, have you seen any other culprits, let's say, that pop up to the top of the list from the magic stuff that happened behind the scenes?
Upcache resets, which you see in file compilation. This thing here, like, it's not doing any file compilation anymore, at least in that minute. So you don't see it in here, but we've seen upcache resets is a good chunk. Like, honestly, most of the customers, or a lot of customers that we have, and we look at the data and try to aggregate that, is that a lot of customers do not run with upcache, and I have no idea why you would run without upcache, but a lot of people do. And what they see is, they see a big red block up on here, PHP always file compiling. That is, if you disable opcache, what you usually see is like 60% of your CPU time spent in file compilation. So you don't want that. If you have an opcache restart, that's a problem. I've seen this, that customers have periodic restarts every few minutes because it's an append-only cache. So it's basically just not configured correctly. You just need to give it more memory. That is the thing. The other thing is garbage collection, that people don't necessarily look at this. And even in this is not something special. This is just a Symfony, I think it's a Symfony demo application running in FrankenPHP worker mode. You can see even this is throwing 30,000 exceptions. I have no idea what for, but it's throwing a lot of exceptions.
And kind of a follow-up question. If I got it correctly, the opcache is clear. You said when there are a lot of roots and you go over a specific number.
That's the GC, the garbage collector. Yeah, so if you create, every time you create an object, that new object will be registered in the garbage collector because it could hold references to something. And then when you have 10,000 roots, so 10,000 objects that qualify for, they could have references to something else, or like cyclomatic references, when you create a new one, it'll add it to the GC, and the GC sees that I have 10,000 roots now, so I'm deciding to do a garbage collection cycle.
Because you said that you can see it in the code what triggered it.
Yep.
But if like something else causes the roots to increase, and you just saw the n+1 that triggered the collection, how do you know that like something before kind of put us in a bad place?
That is the beauty of statistics, because sooner or later it will show up, and it will be the thing that shows up the most. You're welcome. I have another elephant for you. You're lucky. Any other questions? Yeah. I have more elephants.
You mentioned that you take profiling samples and put them into an LLM.
Yep.
Do you prepare the data somehow? Because an XDebug profiling file is fairly large.
No, I just told my clanker to extract the data that it needs. For the Datadog profiler emits pprof files, so you can configure it to not upload somewhere, but to just dump it on the file system. And then you have pprof files, and there is pprof tooling from Go out there. And then you can tell your clanker to just like, there's a pprof file, check the profiles in there. And I have no idea what it does. It wastes probably a ton of tokens, but it's not reading the binary. It's just using some tooling to extract data that's most interesting.
So you're not piping the raw data into the LLM, but
No, I just show it like there's a cache grind file or there's a pprof file, use the pprof binary that I've installed to extract the stuff. And for cache grind, I'm not 100% sure, but for pprof, you have some sorting stuff in there. So you can tell the pprof binary to, that is the pprof file, give me the CPU sample type and sort it by whatever and give me just the top 10. Then the output is just small. I have 2 more elephants. Yeah.
I want to ask, we're currently using XDebug for internal debugging and everything, and problematic would be that for us to use SPX would be extremely hard, because I'm just one of the code, and it would be hard to basically show someone in an upper engineering position to use it. Would you still recommend XDebug, even if we talk that SPX is better, or?
So with SPX, you get a nice web UI. That is something I think is really important. The cache grind tooling is not too nice. Also, SPX creates flame graphs, but that is like some people don't like to read flame graphs. Some people really like call graphs. Then Kcache grind creates those. But I would probably use SPX for it. One of the problems with the XDebug profiler is that its overhead is so high that it's easily 3 or 4x overhead that you get by just using that as a profiler. And that also means that it is biased towards deeper stack traces. So the deeper the stack trace is, the longer its own overhead is to collect the stack trace and create all the data. So it skews the data a bit. So if your stack traces are not 85 frames deep and you're throwing a lot of exceptions, it's probably a problem too that you can ignore. So you can just use that. If you say that is the thing that you have, then I would say use it. That's the best advice, I guess. Just use what you have, and if you find there is some problems in there, then check out something else. But I would start with the XDebug profiler. Was it fun? Yeah. Yes? Oh, yes, it can. Yes, you're right. So maybe if you have a JetBrains license, right, PHP Storm can open cache grant files. That's correct. That's the last elephant. Yeah. Yeah, sure.
Do you know any legitimate reason to force a counter election?
FrankenPHP is doing, not FrankenPHP, I think the Symfony demo application is actually doing it on the teardown of every request if you run it with FrankenPHP or what's the other one? Laravel Horizon. It's also, I think, some process manager or request manager. Then at the teardown of a request, they do a cheesy cycle or they trigger that. The reason for that is you would like to have that happen while no request is in flight because your customer would wait for that. So you do it after the request shut down. That means that for the time you're doing GC cycle, you won't be able to answer to a new request, but at least you will not waste all the time in that request for the customer, because latency is the thing that you don't want to do. I mean, that's the whole thing of a profiler. You're wasting CPU cycles to get some observability, but you don't want to waste latency. So, because you can buy CPU, you can buy memory, but latency is gone. I guess we reached our end. I don't have any elephants anymore. Thank you all for attending.